Look good. Hello everyone. My name is Chia-Che Tsai. I'm now a graduate student in Stony Brook University, and I will soon join UC Berkeley as a postdoc. And also, I'm gonna join in Texas A&M as a faculty in 2019. So, if you're interested in joining Texas A&M as well as a grad student, I would like to talk sometimes if you want. Anyway, today I would like to talk about some system view, system perspective about this software, especially how do we make application working on this very good hardwares. And the point is there's a lot of research. This is a very hot area, and there's a lot of research happening in this area. So I think it would be good to have an overview of all the related work in this area. So I'm not just going to talk about my work, but also talk about all the other works that's related in this area as well. Right. And this is just a legal disclaimer. So some of the material actually come from Intel. So this is just saying that Intel is not responsible for this. This is just for educational purpose. Okay, let's skip this. All right. So the point is so how do we actually develop SGX applications? And so at the beginning, like Jichang talked about, there's SDK model. There's actually several SDK out there. There's Intel SDK. There's also under Rust SDK and also SDK that I heard Baidu is also maintaining one. So you can actually go with this model if you have plenty of time and you want to build your own SGX applications. But there's also another model because there's a lot of application that is already out there and people are already familiar with it and already test them for a long time. So you might want to think about porting an existing application into SGXs. Well, that sounds like a good idea, although there's actually several limitations you're gonna run into if you're trying to do this. So the first limitation is anything you want to run inside Enclave, they need to have assigned a static image so they can guarantee their integrity. So that means that if you have a dynamic linked binary, you won't be able to move it into the Enclave. Second limitation is this Enclave itself is actually a virtualized ISA. It means that there's a few instructions was actually not allowed inside this Enclave because security reason. For example, CPID, RDTSC, like these, you have to get rid of them inside your binary. And these just engineering problem. But the last limitation is the biggest problem is actually security problem is inside Enclave, you actually don't have trusted open system services that you can get. For example, you cannot have system call because you just couldn't trust system call that come from outside of the Enclave. And so if you really want to solve this problem, you need to actually have build defenses against these untrusted open system, but still obtain open system services as you want it. So that is the main problem we're going to solve today. So in general, there's a lot of work that is in this area. A lot of people try to deal with this problem. And so my suggestion at the beginning of this talk is actually we should choose your porting strategy accordingly. So according to what kind of application you're porting, you should look into different kind of framework. For example, if you first you have to think about is how much OS functionality you actually need in your application. If you have something that's you really need very little amount of OS functionality, for example, you're just porting a crypto functions, well, you might as well just use SDK, just port it yourself. But if you need some more functionality, for example, you are building a microservices like a Lightning server, SQLite server, you might want to think about using one of the shielding layer, which I will explain what are these solutions later. And if you are really heavily using some OS functionality, and for example, you're using a language runtime like Python, like R, even like Java virtual machines, then you should think about library OSs. And beside this, you also have to think about whether you actually have a secure unclave interface to the untrusted open system. As I said, open systems are not trusted in this scenario. So they will you have to consider you always consider them as malicious. They will try whatever they can to attack your application. So you have to ensure you have a secure interface. And last, people always care about performance in these cases. So you have to think about whether you'll get too much overhead when you're running these applications. So today, these are the topics I want to cover. First, I'm going to talk about some porting challenges and OS attack vector you're gonna run into when you are trying to port application. And then I'm going to talk about a few work. And notice that here I only talk about the work that is already released out there, so you can download it or try to obtain on your own to actually use them. And also we're talking Linux application. So we're not going to talk about Haven here because it's Windows application and also it's not released. And so first of all, we're going to talk about libraries, which is Graphene-SGX, which is the work we released about 2 years ago, and now it was published in ATC 2017. And then we'll talk about some shielding layer to actually provide system interface directly inside your enclave. For example, there's SCONE in OSDI 2016 and Panoply NDSs this year. And also, we're going to talk about in the next generation of SGXs, in other words, SGX2, they have this dynamic page management, which is a lot of people was sort of asking, what is this actually doing? Well, we're going to show it today and how it works with graphing as well. And eventually, you'll talk about a very good work called Alias actually improve your performance of your enclave. So for all this work, I'm going to talk about what are the target application, what is the key concept that's trying to solve, and also what do you expect? Like, what do you have to expect? How do you actually use those software? And so I'll try to show some demos, and also how do you actually obtain this software? So if you're really interested about it. All right, so let's first talk about what kind of challenges you're going to run into if you try to port application into SGXs. So first of all, any application to run inside Enclave, there's some requirements, and you have to satisfy these requirements. So that would be the first challenge, is just solving compatibility issues. But second, because open system is untrusted, you have to think about the defenses against these untrusted OS services. And third, what kind of performance factor you're going to run into, and we have to think of improving it. So first, application challenge requirement. So thinking about any kind of application, it could be legacy application or the application you're building. Any application will have to satisfy these requirements. So think about how the enclave actually work. When you create an enclave, these enclave essentially you start with untrusted application, and this untrusted application gives the untrusted open system some kind of initial image of your enclave, and also some security measurements. I'm sorry. That's okay. Okay. And some kind of security measurements. And this untrusted open system will use SGX's service system side instruction to create these abstraction called Enclave. And inside Enclave, you run the code and applications to be completely isolated from the open system. But in these cases, there are 3 requirements you have to satisfy. First, you need to have a static initial image, so you can sign it, and you will have a static signature. Second, you cannot make any system call because Enclave is supposed to be completely isolated from the open systems, so they basically just forbid any system call instruction that's actually happening inside Enclave. But third, if you really want some system call, you can jump out Enclave as you want, but when you do that, you have to make sure you check the untrusted input when you come back from the untrusted open systems. And so all the application SGX has to satisfy these requirements that become a big challenges for most Linux application. So first of all, most of these applications are actually dynamically linked against like libc or other libraries. Actually, a survey actually shows that more than 99% of Ubuntu application actually are dynamically linked binary. So you have to solve that problem first. Second, there are a lot of built-in system call usage inside these applications. I'm not necessarily talking about system call instructions, but system call maybe through libc or any kind of system interfaces, you will have to try to solve these problems. So let's see a practical example. For example, let's say you want to port Apache web server to an Enclave. Well, the first thing you have to think about is how do we statically link all the binary? Well, it's difficult because Apache web server use a lot of dynamic linking. They load all these modules and libraries, and you have to solve these problems. Second, you have to bypass some instructions like CPU ID or RDDSC. These usually happen in libc or pthreads, and so you have to go in there and schedule them. And the third part is the most difficult part is also security challenges. Is if you want to exit Enclave for obtaining any system call, you have to think about how to defense against untrusted open systems. And so we'll talk about them one more. We'll talk about it later. All right. So how do we actually defend against untrusted open services? It becomes a key issues here. Well, first we have to think about what kind of attack we're dealing with here when we are running application on untrusted open system. Well, there's a specific kind of attack called EACL attacks, was being reported back in 2013. And this is not even specific to SGXs. This is actually to any kind of scenario when you have untrusted open system and a hypervisor sitting in the bottoms trying to check your system calls. Like there are cases it's actually like intact or overshadows. And so you can think about these cases like if assume you have an Apache web server that's running inside Enclave and they need to make some system call, like a read system call, and you jump out Enclave. Well, what's gonna happen is untrusted open system can return any return value they want or return any data they want. So they will return some kind of data and some kind of sizes, which is might be like exactly the same as the size you want or slightly smaller. Well, anyway, so the point is, untrusted open system is going to manipulate these results to make sure they can exploit the bugs inside your applications and attack your applications and maybe compromise the integrity or compromise confidentiality. And so now we run into this vulnerability that we don't even know how to deal with right now. Basically, in a nutshell, what Yaku attack is a kind of semantic attack that was based on manipulating system call results. So it's very hard to predict where it actually come from or how to actually defend it. Second is usually application specific, so you cannot really defend it from the open system point of view because every application might have different kind of Yaku attack bugs. The third, these kind of bugs does not exist when you're running on a trusted open system. So if you have Apache web server have been running on a trusted open system for decades, there's no guarantee they'll be safe if you move it into Enclave. And these kind of attack make Yaku attack really hard to deal with. So let me show one example of Yaku attacks and show why it's difficult to deal with. So this is an example actually exists in Apache web server in the SSL module. So inside SSL module, when you start a SSL module, they had to first initialize the entropy pool and also initialize your random generators, right? So it's very common they'll give a random C to this random generator. Well, in the current SSL module design, you will see they actually use system time, and PID as the C to your random generator. That means like if you run this thing codes on the untrusted open system could actually always give you the same PID and same time and make your random generator always generate the same random number. So that actually could generate a replay attacks on your Apache web server. So that means this module does not think about untrusted open system at the first place. So that brings the security challenges to porting any application to the Enclave. Okay, so now we have to think about how to solve this problem. Luckily, there are several works trying to deal with this problem here. And so these frameworks, we call them SGX Shielding Frameworks. And they all try to deal with like these three problems. First, they propose defense against these kind of Yaku attacks. So there are different kinds of strategy, but they eventually ultimate goal is try to defend your application from these kind of attacks. Second, because performance matter, so they always propose performance optimization. Third, they also provide competitive features, or you can call it usability features, so make it really easy to port any application, so you don't have to pay too much effort into doing it. And there's two main approach. One, as Chia-Che has mentioned earlier, is library OSs. Second is shielding layers. And so today we'll mainly talk about these two solutions and show the comparison, make you understand when do you want to pick these things and how do you actually use them. So what are the key factors we should care about when we are picking those? First, we think about what are the shielding mechanisms they are using, especially if you are protecting your application against Yaku attack. What are they actually doing? You have to really understand like what are the mechanisms underlying these frameworks. Second, because this mechanism, what kind of attack surface they are facing? Are you facing very large attack surface or just very narrow interfaces they are protecting? Third, you also have to care about trust computing base. It usually is evaluated in lines of codes or binary sizes. And so in this case, in general, from the perspective of the system, software engineering, which always says if you have a large trust computing base, that means you likely have more bugs. And so having bugs inside Enclave is definitely a very bad thing to have. So you want to have a small trusted computer base if possible. The third, you want to think about if they actually provide OS functionalities that you want. For example, if you need multiprocessing, only a few shielding frameworks actually give you multiprocessing. So you have to use those frameworks if you actually need that functionalities. Okay, so based on these key factors, let's look at these solutions. The first is library assist. So what is library assist? So basically, library assist's idea is they move some of the OS component from the OS kernel into the user spaces. And in these cases, of course, they'll move into Enclave. So in these cases, these OS components could be trusted and also stay inside Enclave with your application. So they can service OS functionality directly inside your Enclave. And so by doing this, they also give you the power of redefining small Enclave interfaces with the security in mind. So here, these Enclave, for example, in Graphene, the Enclave interface is as small as 28 calls. And these 28 calls, we can also like directly look at it and specify the security mechanisms on top of it. So the examples including Havens and Graphene-SGXs. And we'll talk about Graphene-SGX later. The next solution is shielding layers. In these cases, they don't want library OSs inside Enclave because they consider it was large trust computing base. So what they do is they introduce a very thin layer, or you can say shim layers, to shield each API. So for each system call, let's say read system call or write system call, they design a defense around it. And so by doing so, they avoid the library OSs overheads, and also they have likely to have a small TCP. An example is SCONE and Panoply. And we'll also talk about these works later. And so if we compare them, we'll compare Graphene-SGX against SCONE and Panoply. Of course, the approach is library OSs and shielding layers. And if you look at Enclave interfaces, Graphene-SGX always has a fixed interfaces no matter how much functionality you need. You might need 100 system call or 30 system call, it doesn't matter. You always have 28 calls as your Enclave interfaces, and it was exactly the same. For SCONE and Panoply, because they directly defend each system call, so if you need 100 system call, then that's your Enclave interfaces to your open system. You have to consider, are they completely defended? The third is, also the next is the trust computing base. So usually we said SCONE and Panoply, these shielding layers like to have a small trust computing base. But if you actually look at a number, you'll see Graphene-SGX is actually kind of in the same order of magnitude as SCONE and Panoply if you just look at library OSs itself, the shielding layers. And so Graphene has 53,000 lines of code, SCONE has 97,000 lines of code, and Panoply is especially small. It has only 10,000 lines of code, which is also reasonable for doing things like verifications. And so you see the actually highest order bit is actually in what kind of libc you want to use. So if you use something like glibc, you're going to be really expensive. You're going to have millions of lines of code in your Enclave. If you use something like Muscle, which is really small, you will have only 88,000 lines of code in there. And also Graphene-SGX could use Muscle if you actually wanted it. Yeah. And Panoply actually just get rid of libc and they expel libc from your Enclave. And so last challenges is the performance factor. There's several performance factors you'll run into your porting your Enclave. First of all, you have to think about the Enclave creation time. Usually, Enclave creation time is correlated. It's not proportional, but correlated with your Enclave memory size. And based on our experience, if you really have to create a very large Enclave, like 1 GB Enclave, because the EPC size limitation, usually is 128 megabytes. I mean, 100 gigabytes you have to swap several times before you actually create an Enclave. So that means that roughly will require around 3 seconds, which is really slow when you create any Enclave. Besides that, you also have memory access overhead. Means so whenever memory has to leave the last level caches to go into the main memory, or going from the main memory to the last level caches, there is the overhead of encryption and decryption. And this overhead could be up to 10 times of the regular memory access. And so that is very expensive. But even more expensive is EBC paging. As I said, there's 128 megabyte shares among all enclave. So if you have to use more memory, you have to evict some pages from your enclave and page in the memory from a swap's devices. And that overall take around 40,000 cycles. This is based on the number reported by Alias. And finally, as Jichang also mentions, Enclave is very expensive. Whenever you jump out of Enclave and re-enter Enclave, overall you could take around 7,000 to 8,000 cycles. So all you have to think about, really have to think about is how do you reduce all these Enclave creation time, memory access overhead, and also Enclave exits when you are developing your applications. So there's two works we're gonna mention today. One is EDMM, Enclave Dynamic Management, which is allow you to add pages, so you don't have to allocate so many pages and creation. So that basically cut your Enclave creation time in half or even more. The second work is Alias. Basically, they identify all these Enclave exits that could cause high overhead, and they get rid of it. So they basically create completely exitless Enclave. The Enclave is just not going to make any exit at all, and including implicit exit caused by page fall, for example, caused by paging overhead. So they have a way of doing software-based paging to make sure that Enclave exits will never happen. Then we'll talk about this as well. All right. Sorry, this is 20 minutes. All right, so let's first talk about Graphene-SGXs. And also use this as this also is a good example to show how does a shielding framework could protect your application from untrusted open systems. So what Graphene-SGX is basically a library OS to help you run a modified application. So a modified application is really its target. You don't have to recompile or modify any part of the application. You can just move it. You can just grab an application from your Ubuntu installation and directly run inside your enclave. And so far it has been supporting all kinds of different kind of applications, from server applications, Apache or NGX, or command line applications like GCC or Pythons, or even runtimes like OpenJDKs. And so it tries to support a wider range of application. It also support a wide range of multi-process APIs, including forking, executes, ESEC, and IPC, inter-process communication. In this case, if you have multiple processes, each process actually runs on individual enclaves. And it does not mean to be perfect, so it still have performance overhead and also other things. It also have limitation of this functionality we don't support, but it's meant to be a quick practical porting options if you just want to quickly try out how SGXs actually look like. So the whole project started with the Graphene Library OS project, which is being published in Eurosys 2014. And we started as an open library OS if you want to reuse any unmodified application. So it's not just for SGXs, it's for a lot of different kind of framework. And so far we've been trying to port into Linux, Windows previously, or even something like barrelfishes or microkernels. And so here, it originally was inspired by Drawbridge, which is the Windows versions of library OS, and tried to run Windows applications and later it was inspired by Haven to use in SGX. And right now so you can imagine how it work is basically inside each process, inside each model application, you have all these processes, and using these processes, they will use system call. And so far we support 145 system calls inside your processes, and this number is still growing. And we create a library OS being loaded into each process to serve these system calls. And these library OS is supposed to be easy to port to any new OS platforms, including SGX is talking about. And so it turned out this design was very suitable for SGXs, including solving a lot of different challenges, including multi-process challenges we talked about before. And so so how do you actually run application inside Graphene-SGXs? Well, Graphene-SGXs provide you a loaders to run any binary that exists on your disk. So first, you just specify, okay, I want to run Graphene loaders with, let's say, right now we're running on HTTPD. You just run it. with arguments you want and turn on SGX's mode. In these cases, they'll create Enclave for you, and they not only run into the first challenge, which is try to have a static initial image. And here, Graphene provides you a signing tool, which is you have to run it on a trusted host. They will take all the binary, including application binary and library and glibc, and also a manifest file to specify your user policy. It would generate Enclave measurement to verify your applications. And this Enclave measurement is unique to your application. So if you have a completely different application, if any binary was different, the Enclave measurement will be completely different. And this Enclave measurement will be verified by the CPU to make sure your application is correct, and also could be attested using remote attestation. And then the second challenge is try to solve the system call problems. Well, now LibreOS actually modified the glibc to redirect all the system calls from the applications, and so these system calls will go to the Graphene LibreOS, and Graphene OS will try to surface them inside Enclave. But if they couldn't, if let's say you have to access like file systems or network stack, they would jump on Enclave using Enclave interfaces. And there are 28 calls inside our Enclave interfaces, which is fixed and easy to check. No, you never. So basically, we just rewrite all the system call as function calls, right? So if it don't jump to Enclave, it's actually really fast. It just stay inside Enclave. So the third challenge is how to actually check Enclave interfaces. Well, there's several arguments I try to make here. First, we reduce the Enclave interfaces to 28 calls. So if you care about your security, these are the 28 calls you should look into and try to verify, make sure there's no vulnerabilities could affect your application at all. The second, we also build defenses for each calls, and there's a few insights of how to do it. First, you can define your API in whatever way that's secure. In this cases, we believe if you have explicit semantics, it's likely to be more secure. That means you know exactly what kind of input you want to check against the untrusted operating system. So you can redefine your interfaces in the way that's easy to check. And then finally, there are crypto techniques like including encryption and authentication that you can use to do these things. And I'm going to show the example of how doing that. So the example I'm going to show is we protect the access to integrity-sensitive files, such as binaries or configuration files. And there's actually a very cool example, which is process creation. I don't have time to talk about it here, but you can see the paper about it. Basically, the idea is you can build a TLS connection between each enclave, and they use that connections for communication, for inter-process communications, including forking. So let's talk about file integrity check. So assuming you have to use one of these function called or system call, for example, reading of files or mapping a file into a memory, or use DLOpen to dynamically load a library. Okay, if you want to use one of them, these will be services inside LibreOS, and LibreOS use one single Enclave call to service all these functionalities. So this function call is basically said, I want to map certain files outside of Enclave. So it would never map inside Enclave, maybe outside Enclave. And so basically we ask for exactly certain chunk of files inside your file. We don't allow the operating system to return whatever file contents they want to return. Second, we try to verify it by checksum. So there's a checksum of the file if each chunk was being stored inside Enclave, and we'll be able to verify them. And so you use both API changes and also crypto techniques to solve these problems. And this is the overview of all the check we try to put on all of the code. There's 18 of them was fully checked, including reading of files, as we just shown, and also inter-process coordination, as we talked about earlier. We established a TLS connection between processes to do inter-process coordinations. And there also 6 call was completely benign. That means there's just no way open system could attack you at all because they just don't take any input at all. For example, if you just try to yield the thread, we don't even care whether open system actually yield that thread because that was considered what something that open system could do anyway. They can just interrupt your threads anyway, so we don't really consider it as an attack at all. There's only 4 of them as currently unchecked, which is treating as future work, and the consequences is they might cause some kind of denial of services to your applications. And so here's some performance numbers of how it actually look like. So for Apache Web Server, here, because we're trying to show multi-process, so we actually run with 5 pre-fork processes in these cases. And the multi-process model of Apache is really interesting. They actually use IPC Semaphore to coordinate every connection. So every connection you have to do inter-process coordination. So in these cases, if you simply just run Linux or original graphing without SGXs, the cost is actually very close. So I'm sorry, let me explain the experiment. The experiment here is actually we try to increase the request from the clients and concurrency gradually until we hit the highest throughput. So if you see when the latency spike, that's where you hit the highest throughput here. And here in this case, Linux and Graphene without SGX is very close. It's a Graphene-SGX actually had 30% loss on the highest throughput. That means that was actually being bounded by the IPC overhead, by IPC bandwidth. Another case is the one, I'm sorry. Exactly. So developer will have to do it. So developer, we provide this signing tool to you. So developers will specify a manifest file, and then they sign it on a trusted machine. They ship all these manifest files and the checksum to the untrusted machine and running on top of it. Yeah. Oh. They can. So there's other cases they might changes in runtime, but here we're mostly just showing read-only files right now. But sure, I mean for the runtimes, we'll also support readable, writable operations files. I'm sorry. The spike. Okay, so why does it just shoot up? Okay, so basically the experiment here is when you continue to increase the concurrency of the client, there's a point where like there's gonna tip over and the server just not gonna be able to handle anymore. You're gonna have too high of overhead of serving anything. So in this case, the latency will be just too high to that. And you can see that's the same pattern for Linux and Graphene as well. Does that explain your question?
So do they depend on what type of request the client make?
Mm-hmm. Oh, this is just regular. I'm sorry. This is just regular HTTP request. Yeah. There's no SSO here.
Yeah, but what I mean is, for example, a client request, for example, transferring a large amount of data.
Oh yeah. So okay, sure. This is actually Apache Bench. Just continue to download the same like 1 megabyte files. I remember that's the experience.
Right.
Yeah.
Thank you.
Mm-hmm. Yeah, you're right. That's actually really important. Yeah. Thank you. So another case is showing our benchmark. This is for showing the command lines applications and also language runtime. As we can show later, like there are some cases where SGX has very low overhead, lower than 1 times overhead. Well, it's not exactly very low, but more reasonable overhead. There are cases where it is really high, can be as high as 10 times. And based on observation, these are usually memory-intensive workloads. And because the memory overhead of Enclave, you tend to have so much overhead. Especially we observe if you have operations like garbage collection, especially going to impact your application performance. And so this is the current Graphene-SGX features. Right now, it uses glibc by default because you want to support modified Ubuntu applications. But you can also use Muscle if you want. We have tested and then it completely work. It supports a wide range of servers, command lines, and language runtime, and they're already tested, and we already provide you manifest files to run them. And it also supports static binary. So if you have a binary that was static compiled with system call instruction in there, we can also support them, but they will have very high overhead. And it cannot support shared memory. That's just something that LibreOffice was never able to support, but we'll think about it in the future. So here, let me show the demo here, which is try to run GCC on Graphene-SGX. Note that GCC is actually a multi-processor application. So it starts with the generic GCC compiler, and then they go to CC1, and they collect twos, and eventually run the linker, which is LD. And here, we're gonna turn on debug messages, so you'll see a lot of outputs, but you can turn it off, and there will be no output at all. And we'll show a tag. Basically, if we try to modify the GCC binary, let's say we compromise one of the binary, would they complain at all? So that shows this demo. Sorry. Okay, so now first we try to build the loader of Graphene. Okay, now it's built, and now let's go to GCC. So we have GCC code. So here we don't recompile the code. This is GCC, which is directly on the Ubuntu disk. This is the manifest file that's needed. You have to write these manifest files for each application you want to run inside Graphene-SGX. So here, this is specifically for running GCC 4.9. And what's necessary here is you actually specify a whole list of binary you actually want to sign. So here, for example, you have to sign the libc file. You have to sign some other library like GCC will have been loading, and specify the security policy. And because this is multi-process application, there's also other manifest file for other executable you're running. So this is for LD, which is pretty much the same, but has a different list of trusted library. Okay. Now you have all these manifest file. What you do is now you throw into our signer. Our signer would generate the signature for you. So this is sort of the process of generating the signature, including creating the memory layout for you in the runtime. So now you actually have, and they will create a new manifest file which contains the checksums, which is just shard 256 values of all these binary that you have to verify. So including, like, let's say you have to run libc, libdl, all these things, they will have to be in this manifest file. Okay, so now these are the things you do on the trusted machine. Now you have this manifest file with signatures. Now you move all these binary to untrusted machines. But of course, we're going to test it on the same machine, but assuming from now on it's happening on an untrusted machine. So now you generate a bunch of tokens. So what token was do was basically there is this AES-ND services being running on each untrusted machine. This was architectural enclave being provided by Intel. So Intel actually provides this privileged enclave to sign off your sign off your enclave. So you cannot run it without getting the approval of these Intel's privileged enclave. So this is the step of getting the approval of these enclave. Okay, so now you get all these files, including signatures, including token, including manifest files. There's a lot of them. You don't have to look into these details. But now let's run them inside Graphene. So you could just run GCC manifest file like regular GCC, and to compile this hello world program. So now its execution is running. Okay, it's done. All right, so basically you can, during these execution, you will see the same output being showed up several times. That means there's actually 4 processes being created during this process. So each process will verify your signature and make sure they're correct. And so now we have this 8.outs being compiled, and now you can just run this 8.outs, and you have the hello world programs. Okay, so this is how you run Graphene-SGX if you want it. Let's try to attack it. Right, so assuming you have exactly the same signature, I'm sorry. Oh, that. Oh, God. Can I speed it up? Okay, so now let's try to attack it. So let's try to open the GCC binary and just change it one word inside it, see what happens. And now just change some 4.9 to 4.8. Now you have different binary. They're not supposed to accept this binary at all. So now we recreate this enclave, recreate this token, get approved by the Intel's architecture enclave, and now we try to run it. And what's gonna happen here is you're gonna get rejected because you have an invalid measurement in these cases, because every application will have a unique signature. Now you can change back, and now if you change it back to 4.9 and run it, and get the token again and run it, now it totally works. So you can see even one byte of binary would triggers these invalid measurements and would not allow the attacker to attack your applications. Okay, this is a new work that is for Graphene-SGXs being developed in Intel actually. So what they're trying to do is they actually trying to combine Graphene-SGXs with containers. So that means like you can actually directly convert these Docker images into Enclave and run it inside SGXs. And so the idea was actually really simple. You can just take these Docker files and directly convert them to manifest files that can accept by Graphene-SGXs. And then they'll run Graphene-SGXs using a modified Docker engine. Now, a modified Docker engine will start Graphene-SGX, run inside a container. So you can consider this case is actually a mutual isolation between operating system and application. So operating system was protected by the container, and application was protected by the enclave. And so this is how it was generated. Well, application developer will provide the Docker images, and they will throw into these engines. They call it the GSC engine, Graphene Secure Container Engines, and they will generate images that contains all the binary. And this binary will be run inside Enclave using the Docker images. And so that's quick demos of how this is actually work. I don't know if this text was too small. Can people see it? Too small? So this is the cases of running a Redis servers inside this regular container. And this is also didn't modify anything. They just directly take a Redis Docker images and just directly run inside Enclave. So you started a regular server and start loading it. Right now, this is not running inside SGXs right now. And so what we want to show here is you can actually grab the memory of this Redis process if you're an administrator, and you can find the keywords that is security sensitive. You can just steal it. So right now, if you grab the memory, you actually see the passwords inside of memory. Was it too fast? All right, that's okay. And now if we run Redis inside Graphene-SGX, these problems will go away. So right now, it actually starts a Redis servers inside Graphene-SGXs. What they do is they convert these images going through this process. You see this output. Well, we see this output earlier. Now it was running inside the SGXs. And we do exactly the same attack, try to grab the memory of this process, and we will see nothing. See. So they see the PID was 2017. Wait, this is, oh, it got restarted. I'm sorry, this is, the order was kind of being messed up. Okay, right now it's actually starting in Graphene-SGXs. And it started here. Okay, so now let's grab the memory of this Redis process running inside Graphene-SGXs. and you will be able to not be able to get any pass-throughs at all. So this is, you can consider this is a combination of the container for the compatibility features of Graphene-SGXs. Okay, finally, there's availabilities. So right now it's open source on networks. You can just download it and use it if you would like it. It's currently on the GPL v3, but with switching to LGPL, so you will be able to commercialize it if you want. If you're interested, please contact me or join our Slack channels if you want to talk about it. All right, so this is LibreOS's work. This shows a kind of opposite works of how this actually works. So for SCONE, it's actually trying to achieve a different goal. They're trying to make this layer as lightweight as possible. So in other words, they're trying to create a C libraries with the shielding technique, but doesn't have the LibreOSs. And also, they actually has make a lot of effort trying to make the system call performance as good as possible. So it also shows how they improve that later. So this is the SCONE architecture. You can see it's very obviously different from the LibreOS's work. They have a C library sitting in the bottom, and they have a synchronized system call interfaces to improve the system call performance. And this C library is based on Muscle, so it is as small as you can think of. On top of that, they have some threading libraries to provide like virtual threads creations. And on top of that, you have file season shells and network shells doing pretty much the same thing that Graphene was doing, basically verifying the file content or encrypting the network's payloads. And top of that, you have other libraries and application you can run. And so SCONE basically doesn't have LibreOSs. You just directly go from C library to the untrusted operating system. Well, you can see the system, in this case, the system call overhead actually matter because every system call is actual real system call. They jump on Enclave and do the system calls. So they actually matter. So they actually verify this. If you look at the throughputs of the system call, if your native system call just doesn't have Enclave at all, it's actually a lot faster than if you do it synchronously. In other words, you jump on Enclave, do the system call, and return to the Enclave. And so this gap is actually really huge. You know, at least more than an order of magnitude difference. And so they want to mitigate this. The idea was just do a synchronous system call. In other words, you don't exit Enclave. Instead, you try to have a queue between the trusted code and untrusted code, and they use that to do the system call without exiting Enclave. And here you see a synchronous system call was in the middle. It's actually a lot closer to the native system calls. Except in these cases where it might be slightly more slower, but still a lot better than the synchronous system calls. So you can see the overhead, and interestingly, you can compare this with the Apache number on Graphene I showed earlier. So for them, you can see the synchronous and native, the gap between the synchronous system call and native system call is quite huge, and this is also was backed by our evaluation of Graphene as well, because Graphene also use synchronous Enclave interfaces. But if you use asynchronous interfaces, it will be a lot smaller. This gap will be a lot smaller. So case of Memcached throughputs. So if you run the Memcached, the throughputs of using asynchronous system call and synchronous system call is actually quite close. And there's another case with using glibc, which will be a lot worse here. So I think this case was basically to argue that using glibc is actually not ideal. Sorry. So should we give the breaks or? Okay, sure. So let me finish this small section here. And okay. So if you want to use SCONE right now actually has languages, a lot of language support. They provide cross-compiler to let you compile any applications. So they have C, C++, Go, Rust, Python, and PHP. And they have partial support with Java, which is still work in progress, but it's still working on it. And so this is a very, very short video just show you how to use that. So assume you have a hello world program, and you just use this SCONE GCC, which is their cross compiler, to compile hello world program, which will give you a binary. This binary can be run in native Linux, which will look exactly like native, But if you run inside Enclave mode, sorry. So you enable the Enclave modes. Now they run inside the Enclave and also show the hello world. So it's very simple. You just use the cross compiler. They should solve all the problem for you. Right now, it can support both static linking and dynamic linking, and also support unmodified binaries, just like Graphene. But if you want to support unmodified binary, you need to have position-independent binary. So you have to compile everything with -f-pic. If you know what it is, there's a flag for GCC to make it position-independent. And you have to be compatible with muscle. So if you're not muscle compatible, your binary cannot run in there. And it doesn't have multi-process at all, so doesn't have fork and doesn't have ESCVEs. And you also have Docker integrations, just like what we try to do in Intel with Graphene as well. And so it also supports converting Docker files into images, into containers, and also convert it into Enclave, so they can run it just integrate with Docker, very simple, and you can use multiple Docker engines to run it. So finally, availabilities. So if you want to use SCONE, SCONE is actually not open source, so it's commercially available. So if you're interested, you can visit their websites and you can obtain it by asking. You can request the software if you want it. All right. So we have last section. We have to talk about Graphene SGXs, and which is LibreOS's approach, and also SCONE, which is the shielding layers approach. We're going to see another works, which is also shielding layers approach, but they take even a very different trade-off here. So the idea of Panoply here is basically you try to provide POSIX API using glibc, but does not include glibc itself inside the trusted computing. In other words, the whole glibc will be outside the Enclave, which is different decisions being made by LibreOS and SCONE as well here. And so the idea is to have a very small TCP, and so there's TCP overall is around 10,000 lines of code, and this is the code you have to verify if you want to use these softwares. So this is the idea. This is their ideas. The idea is to actually create these. They call them the micro container or micron to run any kind of Enclave logics. So these Enclave logic will be sitting inside Enclave with some kind of Enclave bound logic. You can think about is the same shielding logic that we have in Graphene and SCONE as well. And below it, you had a shim library or a shim library to forward everything into Enclave, and also they use a trusted SGX library that comes from the SGX's SDK. Right. And below it, they have glibc that's outside Enclave and has all the other codes that you don't have to trust at all. So the code that inside Enclave was simply just your applications and this very thin layers and SGX's SDK libraries. And I think the key contribution that Panoply have is they actually don't necessarily bound these frameworks on one application, but also on libraries. So you can actually imagine inside an application you have several libraries you might be using. Then you could actually create multiple Enclave to protect each libraries. So they actually provide a multi-Enclave collaboration model. Imagine here you have the solution. You have a web server that use SSL library. So you can actually run the web server in one Enclave and SSL library in another Enclave. And because, of course, they cannot directly communicate to each other because architecture did not allow you to do that, but you can go through the operating systems to do these communications. And how do they do that? Well, first of all, you can consider the generation here, the model is like this. It's just the same thing as SCONE, you take the source code and make some kind of annotations, and you give it to the compiler they specifically provide you. And they basically generate everything, including change instrument your application to use their API, and also adding all the checks you needed against Untrusted Open System. And then you create an Enclave, including all the binaries that you don't want to put into the Enclave. And so eventually you create several enclave based on your own annotations. So you have enclave 1, enclave 2, and enclave 3. And each enclave could be one libraries or one binaries. And that's what Panoply was providing. And so they have to actually protect these multi-enclave application. You actually could think about this model was similar to the Graphene's multi-process model, where you have two enclave was communicating through the untrusted operating system. So that means you actually have to protect them. Well, how do we do it? Graphene-SGX, we do it in TLS connections. The same thing here, they try to do the same thing. So you can, assuming there were several attacks where operating system could actually do on these multi-enclave communication, including spoofing the messages between the enclave, doing replay attack, or just silently dropping the messages, and so you don't receive any messages between enclave at all. So you have several defenses, including authentications like TLSs, or ensuring message freshness is like make sure you have like randomly created these initial vectors and everything. And so it's sort of similar as the TLS connection we use in graphing as well. Here's a performance overview. So they actually run a very special set of applications like OpenSSL library, H2O, it's a web server, and FreeTDS and Tor actually. And you can see like overhead, the highest overhead is Tor, which reached about 48%. And overall it's sort of in the same order of magnitude as Graphene-SGX's and SCONE as well. And unfortunately, I don't really have a demo for Panoply right now because Panoply required an earlier version of Intel SDK, which is 1.6. But overall, what their feature is, they actually support the whole set of 254 POSIX API. Among these 254 POSIX API, there are 91 of them was completely safe. By safe, you mean they completely guarantee they preserve the API semantics based on their specifications. So you can trust those API. The others are a little bit wild, so you have to consider whether you are using all these APIs. And also they support a version of multiprocessing, including fork and ESEC. And they actually has an interesting way of implementing fork. If you're interested, you can take a look at their papers. So availability is actually open source. You can go download it, play with it. It's Apache license, so you can feel free to do modification as you want. And if you're interested, got any question, please contact Shota, who is the first author of this paper. All right, so we covered the three work, the shielding frameworks work, which is will protect your applications from the untrusted operating system when you are doing these portings. Next, we're going to talk about two work that actually give you performance optimization, which you will really care if you're doing you're porting most of the applications. So the first work is EDMM, which is the Enclave Dynamic Memory Management. And here, the reason why we need this is because the current SGX actually has limitations that doesn't allow you to enlarge your enclave after your enclave was created. So let's say you said your enclave size was 128 megabytes, then it is 120 megabytes during the whole execution of your enclave. There's no way you add more pages or remove pages from it, right? And also there's a fixed amount of threads that you have to create at the very beginning. So let's say you set as 4 threads, there's no way you can use 8 threads if you want, right? And so SGX2 actually solves this problem for you. They actually allow you to add pages at runtime after enclave was created. And this gives you several performance benefits, including reducing the initial enclave memory size, so you don't have to create a very large enclave with lots of memory now. Give you dynamic thread creation, so you can just create threads on demand. And then you have dynamic page protection, so you can protect pages as maybe read-only or executable after enclave was created. And this is very good for dynamic loading for something like LibreOSs, or if you have a JIT compilers inside your enclave. And this will be supported as a future versions of Graphene-SGXs, and we'll be open sourcing it in the future. This is also being done in Intel's right now. So what is the current SGX limitations? So current SGX limitation, because of for integrity, each enclave will have a steady memory layout. That means every pages will affect the enclave measurements or will affect the signature of the enclave, even if the data is not security sensitive. So that means these memory layouts will be designed by users and will have to initialize at runtimes. And so that means if you want to do malloc, do dynamic allocations, you will have to reserve a large enough heap for whatever memory footprints that your application have. And that is an overhead to the creation times. And second is because for each thread, you need to have this data structure called TCS, is thread control structures. And the number of TCS literally equals to the number of threads. So that means because you cannot dynamically allocate memory, you cannot dynamically allocate threads. That was exactly the same problem. So in the next generation of SGXs, they'll solve this problem. And what they solve this problem is they allowed dynamically adding and protecting enclave pages at runtime after enclave was created. And the semantic was very simple. If you want to add pages, basically open system could give a pages to enclave using special instructions. And that is not done because we cannot just let open system do whatever they want. The enclave actually have to approve these additions of the enclave pages. And also this enclave content must be 0, but it could be either normal pages or one of the TCS pages for the use of thread creations. And so we actually use it in Graphene-SGXs. That means we actually largely reduce setup startup times using EDMM. And also we dynamically create threads, so you can have any number of threads you want. And you can protect pages after finishing dynamic loading. Originally, Graphene actually has this limitation where all the pages are actually readable, writable, and executable, which is a potential security threat. Right now, you can protect them after dynamic loadings, and also support system call like mprotect. So let's look at a quick demo here. This is also kind of small here. Okay, let me see. So here we're using Graphene-SGX to run Pythons, and here this is the EDM version of Graphene. So you can actually enable or disable EDMM by changing the manifest file. So here we actually disable it first, and so with disabling it, we run Python directly in Graphene-SGX. I'm sorry, the text might be a little bit small, so I'll try to describe what it's doing. So here you can see they actually have to commit the large heap spaces. Right now it's around 70 megabytes. And these megabytes will have to edit to the enclave every time when enclave was created. And so that actually made the execution time to be a lot more slower. So to run a hello world program, sorry. Let's see if I can let. So to run a hello world program, it takes about 1.5 seconds to finish. Now let's enable this EDMM mode. Sorry. And now we do the exactly same thing, try to run it. Now the heap spaces is not committed anymore. In other words, they are actually, we reserve the spaces, but they are not added to the enclave from the very beginning. And by doing so, the execution time was improved to almost half, around 0.7 seconds. So this is the kind of benefit you can get in the future if you have SGX2 hardware. Okay, let's move on to the next slide. All right, so when it's being available, well, unknown. SGX2 release days, right now we sort of expected it to be in 1 to 2 years based on the rumor inside Intel, but we don't know when it will happen, so nobody knows. But EDMN supports would definitely eventually be open sources as part of Graphene-SGXs. No, this is on internal machines inside Intel. It's real SGX2 machines. Yeah. Okay, this is the final works I'm talking about. This is actually very interesting work, especially targeting the performance optimization. And they do a very good, thorough survey of what is the overhead of enclaves to actually come from. And so they actually deal with them. And they have a very great solution for them for dealing with this overhead. So think about what kind of costs that Enclave could have when you are running some applications on Enclave. First, you have Enclave entering and exit costs, which is each around 3,000 cycles to 4,000 cycles, which is a lot more expensive than one system call, because one system call is just around 250 cycles. That's the first overhead you run into. The second overhead is last level cache misses. As we said earlier, you can't if you miss something in the last level caches, you have to go to the main memory and access one of the EPC page. And accessing these EPC page requires decrypting them on the way back to the last level caches, which is introduce around 5 to 10 time overhead to the memory access. And finally, there's EPC paging, because there's 128 megabytes memory was given to all the enclaves. So if you have to use more than that, there's 40,000 cycles going to be spent on evicting any pages that's currently in the enclave and page in another enclave pages. So all these overhead you can expect from basically exiting enclaves or entering enclaves or using memory more than the EPC could handle. But there's actually other overhead like indirect costs. The first indirect cost is last level cache pollutions. I mean, because your last level caches also share with untrusted codes and also other CPU core. That means if other CPUs use most of the last level caches, you're gonna also have a significant overhead because of last cache misses overhead. So here they actually do an experiment using a key value store servers, and imagine if you have more data being processed in each request, in other words, has more pollution into last level caches, at most you can have up to 2 times slowdown if your last level cache is heavily polluted. And so that is an indirect cost you can consider when you're running inside Enclave. Another indirect cost is TLP pollution. So what happened here is every time when you exit Enclave, you have to essentially flush the TLP. Well, TLP, if you don't know what TLP is, TLP basically is a quick mapping inside the CPU for your page addresses from the virtual address to the physical address. So every time you have to flush these things when they jump out of Enclave, and every time it flushes, you cause huge overhead. And so here they also do experiments with the same key value store, but use 2 different collision resolution approaches in their hash tables. So one is sensitive to the TLP flushes, and one is insensitive to it. You can say the one that is sensitive to TLP flushes could actually have up to 6 times overhead than the one that is insensitive to TLP flushes. So we see 2 indirect costs and 3 kind of direct costs could totally affect the performance of your applications. So what do we do with it? Well, the simple answer is Enclave exit is bad. Either it was explicitly exited by your applications or implicitly exited because your page fault. So here, they actually try to deal with both problems. First, they try to get rid of explicit Enclave exits by creating an RPC-based Enclave interfaces, and this is built into the Intel SDK. Basically, they they modify the Intel SDK and to make them automatically generate all these interfaces, which is RPC-based. In other words, they don't jump on Enclave; they simply communicate through RPC queue. And if this look any familiar, this kind of look like the asynchronous system calls of SCONEs. Another very cool thing here is, well, now they also want to prevent the Enclave exits caused by page fault. So if you want to use more than 128 megabyte memory, they have a way to prevent you from exiting Enclave to do swapping. And so here the idea was to do a user space in swapping. So instead of relying on the page table outside Enclave, they actually have the software simulations of the page table. So they have a software address translation happening on Enclave, which just have a page table maintained inside it. So they can actually have has pinned fixed numbers of Enclave memory inside the Enclave, and these Enclave memory would never be swapped at all. But they can do software swappings inside Enclave, and they will softwarely encrypted into another part of your DRAM. And so by doing so, they make the amount of EPC pages being used by the Enclave was fixed, and to avoid any Enclave exits caused by page faults. And originally there's some demo I'm showing here, but I'm gonna skip them. Basically here what they show is just running Memcached with three different modes. One is running in native SGXs, they put into SGXs. The third mode is basically running with RPC optimization, and thermal is RPC plus the software virtual memory paging. And here is the result. And the result here is very obvious. When you have used alias RPC, they actually improve 23% of your performance. If you use both RPC plus SUVM, you actually has 50% improvements, which is pretty significant if you consider it. And this is also available online. This is open source, so if you're interested, please download it and play with it. Or if you have any question, please contact the authors about it. And so that's pretty much the end of my talk. And finally, I want to acknowledge just that these are all the people has helped me create all these slides. They also the first author, last author of these papers.